So yes, so quick word from our sponsors. Yes, I am part of Arup in the Oasis software group of Arup Systems. It's a short form, part of Arup Digital, and it was originally formed back in 1976 because back in the 1970s, consulting engineers were not allowed to advertise under the regulations, so they formed the separate Oasis brands. And these days, yeah, we do structural software, which is my main interest. There's also geotechnical and the pedestrian simulation stuff. And other sponsor, IStructE itself. As I said, last October I published book Computational Engineering, which is covers a very wide range of topics on essentially everything that structural engineers need to know about computing, at least at a moderate level. And with the idea then is, if there's anything that you want to go, I want to know more about this, then there are more detailed tomes that you can then get into. Now, certainly in that book I have 2 chapters on optimization, and this talk is a sort of summary of some of the things that we talk about in those chapters. But so great if you're a graduate or a practicing engineer. It's also quite good if you're of a more senior level and want to have some idea of what earth these youngsters are up to these days. So, design optimization itself. Now, the design optimization is an expression which has a lot of meanings, not meanings. Now, and if you ask most people, that they'll give you 1 or maybe 2, but I'm going to take you through a range of options and methods that are used in design optimization, that you can use, that are being used, and so on. You may have come across some of these methods or may have heard of them, in which case it's a big revision. Anything new? Well, it's new options. And yeah, so there are many ways to optimize your design. And of course, yeah, so now optimization. All talks, all papers on optimization are required by law to show the formula, this FX formula over here. Unfortunately, it's virtually meaningless, but it basically says that we're trying to find the best solution amongst the set of all feasible solutions, or at least a subset of feasible solutions. And this means that you need to have, well, feasible solutions take into account various constraints. So you need to have an objective. What are you trying to minimize? Least cost, least weight, the correct stiffness, minimal environmental impact. Then the variables you need to consider. Are you looking at section size, nodal locations, number of beams, connections, and or not? And then what are the constraints? Yeah, obviously structural engineering, allowable stresses, section strength capacities, deflection limits, and that sort of thing. Now, in case of this talk, for example, I've tried to optimize the content of this talk, aiming to maximize technical content, usefulness, interest, with the constraint of a 1-hour delivery. And of course, with all multi-objective optimizations, the result will be a compromise of, with 1 or 2 or maybe all the objectives falling short, but like all good engineering, hopefully being close enough without falling over. We shall see. So, types of optimization problems you may deal with. Continuous optimization versus discrete. So continuous optimization might be a concrete beam size. We can make it any size you want. But discrete optimization is steel beam sizes. There are limited sizes in the catalogue. If you're doing plate goods, there are limited plate sizes and so on. We can have problems which are unconstrained or constrained. Now, strictly speaking, all structural engineering optimizations are ultimately constrained in that they can't fall over. But when you're doing an optimization, you may want to be more flexible about that and say, well, the design might temporarily be, this design might be failing, but it's not failing as badly as another design, and so it's a little bit better, and you might use this sort of unconstrained idea to take you closer to the final answer. Numbers of objectives. Yeah, that all design is a compromise. If you're dealing with one objective, let's say least cost or least weight, then yeah, you can be pretty sure you can get the definite answer, or at least a pretty good answer. When you're dealing with multiple objectives, like least weight of steelwork versus plus least number of beams to minimize the connections, then the compromise, or well, we'll look at some other multi objectives in the presentation here. And there's also deterministic versus stochastic, which generally comes down to linear versus non-linear, or I mean, deterministic, we can determine what the answer is. Stochastic involves randomness, which seems a strange thing to add in, but there are a number of optimization techniques that we'll look at, that is actually quite useful to include randomness in there. It all depends on the sort of problem you're dealing with. Okay, and what can we design? Well, what can we optimize? There are the section or size optimization. What is the best section sizes to choose to get the least weight? This is quite often what people mostly think about, but this is actually optimization which has the least end effect. So there's the shape optimization, optimizing maybe the plate girder shape, but maybe optimizing the truss shape layout. How high does the portal get frame go? What's its slope? And how deep is the truss, and that sort of thing. And then there's topology optimization, which is throwing everything out there. If we're doing a truss, how many elements are there in the truss? In the building, how many columns? Which way are we spanning? It's possibly the hardest optimization, but the topology optimization is the optimization which will have the biggest end effect on the end results. So really the section optimization is really the fine tuning you do at the end, and I've deliberately given this list in reverse order. You should normally be working up and not down. And which one's which? Well, as you see, optimizations, exactly where optimizations fall in these categories is a bit fuzzy. Maybe it's not too important, but it's good to understand the concepts, and alternatively, of course, you can have a good argument as to which is which. And of course, yeah, the main thing with all these optimizations is why we're doing it, and all engineers, we want to produce structures which are as efficient as possible, particularly relating to carbon net zero. Now, as an industry, we are responsible for about 8% of the world's greenhouse gases. The environmental impact of steel production, of concrete production. Similarly, sand and gravel these days are in such demand for concrete around the world that organised crime is taking quite a large part, and they're actually a major supplier of concrete materials these days, with cases of entire beaches and islands being stolen through illegal dredging, which then leads to flooding, habitat loss, water supplies, even more demands. I mean, water shortages in the last decade have caused over 200 violent conflicts around the world. The more we can do to reduce all this which goes into our construction designs, the better is for everybody. We have to use less materials. And also, of course, for clients want the design to be as cheap as possible while still maintaining standards and safety and so on. And we're engineers. We like the challenge of achieving the goal with the least structure at the end. So we must learn to do more with less. So concepts you need to think about. One of the first, and I think the most important, possibly in optimization, is that concept of the search space or the design space. Now, this design space is the range of options. So, an example, here we have a very simple structure, a crucifix of steel beams, all the same length, fully connected in the middle with a central point load. Very, very simple structure. And here the design space is the range of all possible beam sizes that we can use. And if we consider one beam from the smallest to the largest, and the other beam to the smallest and largest, and we can plot these as a grid. And so this is design space, a range of possible alternatives. And if we decided we're going to build this structure with both beams the same particular size, or whatever, there's a particular location in the design space where we have those two beams represented. If the beams are both the same size, then they'll both extract the same loads, and hence each beam will work equally hard. But maybe I'm sure I've noticed that that's only one of the possible solutions. You can have one beam much bigger than the other, so that beam takes all the load, and the other one is just there to give it a bit of bracing and mid-span restraint. And also, actually, there's the other beam. The other beam could be carrying all the load. So actually, for this simple structure, there are three basic answers that we can choose. Now, if we're doing this by hands, we might just pick two section sizes. Having decided, are they going to be the same? Are they going to be different? Analyze them. Design the beams to carry those bending moments. Then reanalyze to check, because obviously changing stiffnesses can change the moment distribution, but also self-weight of the sections can change the loads and so on. And that might require a new set of sections, and we might find that wherever we start in the design space, that we all sort of end up at a particular answer. So the idea is, if you start off with symmetrical sections, you'll end up with symmetrical sections. If you start with asymmetrical, you'll end up with asymmetrical. And we have these given answers in these locations with a sort of tributary space, tributary area in the design space, which leads to those answers. Now, with this answer, relatively simple, and if we are using British Universal Beams, for those outside the UK, other sections are available. So there are approximately 100 universal beams in the British catalogue. So 2 dimensions, 100 times 100, there are approximately 10,000 possible solutions in the design space, even for a simple case like this. Now, this was my original initial estimate of what the design space tributary areas would look like, and then I wrote a little script which actually ran through all the options And so I discovered it was a lot more complicated than I was expecting. Now, if we see the graph here, or the chart here, the blue spots are choice of beam sections which do end up with the completely symmetrical section, as expected. The orange, peach, go to these orange results here, very asymmetric, but to my surprise, there's also these nearly symmetrical sections, which I didn't expect, but they do work. But which answers you get to very much depends on which sections you choose initially, and if you are choosing manually, you're very likely to still get to those three main answers that I originally said. Interesting enough note as well, for the bit of detail, there were cases where I'd actually get oscillation between two answers. If you are writing your own routines, something worthwhile looking out for. So the design space itself, one of the reasons I wanted to have a model case where we just had two dimensions was to be able to actually visualize and see what the design space actually looks like. We often talk in design space about it being a terrain, having height, and that sort of thing. And so for the design space, I wanted to be able to plot it, and in this case, I've plotted basically the optimization of the pair of sections. In this case, well, rather how close they are to optimum. And so you see there is not just some peaks, there be the symmetrical sections in the middle. We have this sort of ridge, and there's a slope with a few other minor peaks and so on. Now, this was not, I didn't use all the universal beam sections for this chart. I used about 20. If I used all 100 odd beams in the British Steel catalogue, the design space is actually considerably spikier, much rougher, and that's because as the beam weight increases, that does not mean that the moment capacity also increases. Sometimes you get a lower moment capacity for a larger weight. It all depends on the depth to width ratios and that sort of thing. If you imagine, for example, using a universal column as a beam, you know they end up being quite heavy to carry the load, bending moments, but with less depth. And so for the previous example, I actually looked at all the sections, and actually whatever the moment capacity drops with increased weight, I just removed that from my design space. So design space went from 100 by 100 down to about 20 by 20, which, as you can imagine, is a major efficiency improvement in the optimization. Now, this was a case with just two beams, simple, trivial. In fact, real structures are obviously considerably more complicated than that, and being higher complexity, harder to visualize, more difficult to negotiate through the design space, and the answers don't always just drop out like they can do. So more complex examples, especially dealing with multi-moment frames, we're into searching for the answers. And how you search the answers can be quite important. Now, other things to think about. Multi-objective optimizations. Single optimization, there is a definite answer, possibly. With multiple objectives, there are multiple answers, and you have to judge them. Now, the Pareto front is something which was named after Italian economist Vilfredo Pareto, and he had this idea that you can plot the various answers, optimizations, and then there will be a range of acceptable answers, unacceptable answers, and there'll be a sort of boundary between the two, and you can get the various answers, and you can see where they fall onto Pareto front and say maybe which one they want. And I'm looking at that and thinking, well, that's a pretty good one. That sort of reasonably balance between the objectives and so on, and it gives you an idea of how to judge between the two. Now, here's a real example. Now, this is a case from Stanford University where they were looking at optimizing the structure versus construction costs, minimum construction costs versus minimum life cycle costs, with things like the height and the floor area being fixed. And so here is the plot of their Pareto front, and you see the color of the best to worst designs, and the Pareto front is round about here-ish. And yeah, and obviously this is with 2 dimensions. Once you get into 3 dimensions and beyond, visualization becomes a lot harder. So, rhetorical question for you to think about. How does the concept of the design space relate to your projects you're working on? And as a bonus, if you want to put it in the chat, can you name that shape? And if you want a clue, something to do with Marvel movies. Okay, on to the next one. Topology optimization. So, topology, all about the actual layout as a whole. So, example. This example was given by our 2012 president, John Nolan. Give this challenge in this inaugural address. So here, I'm the structural engineer. So here we have this very simple example: a warehouse, 180 meters by 90 meters, 9 meters clear to the underside of the structure, 12 meters maximum height, weak ground, mildly contaminated. What is the cheapest layout? Now, I used to do portal frames a lot, and we would basically work it out by going 6 meter centers. I'm going to span it short distance, hit and miss columns, go. But actually, there are a lot of options we can choose from. We can span the roof in the short direction or the long direction. If we go in the short direction, do we have 4 bays, 3 bays, 2 bays? If we span the long direction, again, between 4 and 9 bays and so on. Do we put columns everywhere, or do we use the hit and miss option to have every other column? If we put moment bases in, that will reduce the steel frame section sizes and weights, but that will require bigger foundations. And we're dealing with contaminated ground. Is that going to be a problem? And you look at all these options, and we've already got over 100 different layout options to choose from, even from just a simple portal frame shed. And so we decided the optimum is 3 by 30 bays. But then we've now got 2 valleys to deal with. Drainage is difficult on portal frames, on valleys. Expensive siphonic drainage. Maybe it'd be cheaper to use a single ridge. Then the lower pitch, standing seam cladding. Yeah, optimization in the real industry is complex, more than just choosing the right section sizes. And there will be aspects outside your own discipline that you'll need to consider. Okay, slightly more modern topology optimization, evolutionary topology optimization. And this method, we can start off with just a mesh of, okay, there's structure in here. What we would then do is just start to trim away the bits which are not doing much. And then analyze and keep trimming and keep trimming, keep removing the bits which are doing least, thin it out, strengthen the hard-working parts and so on, and we end up with a remaining optimum structure. Now, obviously ignoring any lateral loads and that sort of thing in this case. Now, the result, very efficient, and yeah, looks a bit organic. Because this is very much the way that our own bodies work. So bones and muscles, if they get used, they grow. If they don't get used, they get removed, and the bodies don't want to carry around anything which isn't being used. So this is very much like the way that biology works. And this is a script that I wrote, but yeah, quite easy to do your own. And interesting enough, the end results, yeah, so a chap called Mitchell back about 100 years ago, he came up with this idea that you could actually define the most efficient truss. And you can prove that these truss layouts are the most efficient way of designing. And I ran some evolution topology optimizations on these cases, and I took phone app, top opt, just download it for free. Yeah, and these structures do tend to come to fall out. Maybe not always exactly, but yeah, and the obviously real trusses are quite difficult to design like this, a lot of connections and so on. And this can be a starting point for your design for then rationalization afterwards. Now these are very simple examples. Here is an example from Arup in Beijing, where they're looking at tall building bracing arrangements. Again, using an ETO to look at how they might deal with wind loads and seismic loads, and with various parameters about how dense a structure they want and so on. And you can see that these various arrangements, you wouldn't build these directly, but you could then build the truss arrangements and the bracing on the buildings to match these patterns, or at least get close to them. You'll also note that there, and also go back a slide. One of the significant things about these Mitchell trusses is they often feature right angles. There tend to be right angles at each of these connections, and a feature of optimum trusses is the forces have at least the minimum sort of change of direction in them. Now, ETOs, if we could go the whole hog and we go 3D printing, we can end up results like this. This is a case from Arup in Amsterdam. They were doing a very lightweight cable truss roof. And for example, on the connection on the left is what they would normally do. That's what we did first. Steel tube, steel plates, designed by hands, and then realize this is quite heavy. And so let's use an ETO to optimize this, and then use 3D printing. And this is their first answer they come up with. And you notice it's quite similar with the rings, the bolt through and everything. And I thought, well, let's go one step forward, and rather than using side bolts, just screw directly in. And they end up with an even lighter connection with a very organic shape. Now, 3D printing is still in its infancy, but there are projects out there, and this is one you may have seen in the press recently, again from Arup Amsterdam, from a new 3D printed bridge over one of the canals in Amsterdam. This is actually a 3D printed steel, so it's 100% weld. So reduction in material, but probably quite high in embodied carbon. So this is not the final answer. This is a work in progress, but yeah, we will see designs and these sort of techniques being used more and more to enable us to do more efficient designs. And this is both efficient design, it's also sculpture as well. I do speaking within straight across, but yeah, efficiency isn't everything when you're dealing with works in public spaces. So, rhetorical question for you: how might you be applying topology optimizations on your projects? Did you just pick a design and go for it, or are there things you need to be thinking about? What's next? Shape optimization. So shape optimization, working out, okay, the topology of this wheel is the same, what's it, 8 spokes, 6 spokes, whatever I suppose it is. Topology is the same. but then looking at the shapes, the holes, and that sort of thing. Now, how might we optimize shapes? Now, optimizing shapes of trusses, for example, we could use Maxwell's theorem of load paths. James Clerk Maxwell, who you may have come across. When he was not creating structural analysis theories, he was also busy inventing electromagnetism, color photography, thermodynamics, and so on. Yeah, he was a busy chap. So his theorem is if we sum up the length of all the elements multiplied by the forces, either tension or compression on them, and depending on the signs we use, are we using tension and compression with the same sign or opposite signs, depending on whether we use a plus or minus here. If, let's say they have the same sign, if we take the compression elements away from the tension elements, we end up with a constant value, no matter how we sort of vary the truss, which is a bit of a surprise. But ultimately, what we're looking to do is the summation of the length of elements times the force in the elements, get that to a minimum, and that gives us an optimum. Now, you'll note things like this is designing the truss without doing design. Is it steel? Is it concrete? Is it timber? Doesn't matter. We're looking at the layout. There are a few fiddles like buckling, that sort of thing, ignoring those. But also what is interesting to note is that we're minimizing this, but taking one from the other gives us a constant, which means if we want to, we can optimize just the tension elements or just the compression elements. If you're doing it by hand, that's probably a good way forward. If you're doing it by computer, heck, just do them all and have done with it. It's easier to just do them all than try to filter them. So here's an example. This is an SOM project, Exchange House in London, which I think is outside St Pancras Station, I believe. Train tracks going underneath, so they had to actually span the whole building across the train tracks. And so they realized the best way to do it was with a nice big tied arch to support this building frame. Then comes the question, well, how high should the arch go? We know if the arch is very shallow, it's inefficient, very heavy. If it's very high, we've got a lot of length and everything. So they used Maxwell's theorem to look at in this case, do it by hand, looking at just the tension elements. And if you're up with the calculus, you could put that in as a formula, and then work out the minimum from there straight off. If you're doing it by computer, you could just build a model and just vary the height to give you the ideal option. Yeah. Or calculator, depends how you go about it. Now, other shape optimizations, tent structures. So tents have been used for millennia, but it wasn't until late 20th century that engineering architects began to take these quite seriously as engineering structures. So Frei Otto, Munich, 1972, Olympic Park. As a German architect engineer, he really wanted to go complete opposite to the very heavy architecture of Nazi Germany, and so he sort of come up with these designs for the Munich park, and to do these designs, obviously 1972, no computers, it's all done with physical modeling, and you can see some of these examples here. Then with physical model these days, you might use like tights or fine meshes or soap bubbles or that sort of thing to do the modeling, and then very careful measurements, and then lots of calculations to make sure they're get the forces out. These days, obviously, we can computerize this. So tension structures, fabric structures, they tend to come in three basic forms. Always double curved in two directions with the conic, the barrel vault, and the high par. And this double curvature is very important for the stiffness of the section, of the structure. But interesting enough, this double curvature can be found by looking at the minimum surface energy. So we can use methods like soap film, where we represent the fabric structure as a literal soap bubble, zero stiffness, constant tension, and just find where it's where it's happiest. Or there's a method called force density, which is similar, not quite so accurate, a lot quicker, tends to be favoured by the architects because it's close enough for them. But soap film, a little bit closer for us as engineers. And the edge can be a solid ring, like in the photograph there, or it can be a cable edge. And here is one example: Arup project, the Marseillais Tate Modern sculpture by Anish Kapoor, and we have a steel ring here, which is also the weight, which is tensioning up the structure, and the end rings, which is the support structure. And then we have these sort of conic forms in between. And we know that the geometry is correct and the pretensions are correct because these surfaces are smooth. If you get it out of balance in the pretension, the tensions in the fabric, you get wrinkles. As you know, if you ever tried, well, look at my shirt, not quite equal tensions on the shirt. You get these wrinkles. Huygens, or was it Wagner's tension fields? On the two, we get confused between those two. Another example. This is Expedition's 2012 velodrome. So this is a high-power cable net structure, and very lightweight, 60 kilograms a square meter. Also had the advantage that they're actually able to build the roof flat on the ground and then just pull on the end cables and it just sort of pops up into position. Won the IStructE Supreme Award back in 2011. Another example, it's sort of barrel vaults, cable edges, some steel members, cable net supporting, sort of a hybrid fabric structure. You know, like all these structures usually don't fall exactly into categories. This being tennis center, this is a great roof because any balls which land on the roof will just roll straight off again. And it's actually I mentioned the three basic forms of tension structure. There's actually a fourth, which is the inflated structure. So this is the Beijing water cube. Each of these bubbles is an ETFE foil, which is inflated, and that inflation gives a double curvature and thus the stiffnesses. Also, this pattern looks quite random, but in reality, it actually repeated. There was only about 30 different bubbles. It's just it repeats on a diagonal, so it's quite difficult to spot the repeat. So there. Other examples: Mannheim World Garden Exhibition, timber frame or timber grid shell. Again, early 1970s physical models, but you can see how thin the grid shells are. Very efficient for very little material. Or going back even further, physical model hanging chains. This is Sagrada Familia in Barcelona from Antonio Gaudi. And you can see he's using hanging chain models to produce designs. This is from the basement museum there. Get a chance to go over see it. It is awesome. If you get it after 2026 when it's finished, it'll be even more awesome. But you get to see it under construction at the moment. And you can this is a photograph of the interior at the moment. I was there a couple of years ago. Amazing space. I mean, you can see, yeah, these optimal designs, they are quite organic because nature naturally optimizes. Now these are sort of actual sort of catenary structures, but you can just go for parabolas. Parabolas are pretty close to catenaries, not quite exactly the same, but for concrete shell structures, they have some inherent stiffness of their own. and parabolas can be close enough. This is from this one example on the left, 1939. You can get an idea of how thin that shell is from the size of the person standing on the bridge. Now, parabolas have the additional advantage in that they are actually a double ruled surface. And so this is single ruled surface, this is double ruled surface. Being single double ruled means you can form them using straight lines, and that makes the concrete shuttering considerably easier. So, question for you: shape optimization. Think about your projects. Is it applicable just to lightweight structures, or are there other things you could be thinking about shape optimization for? Okay, the classic size or section optimization. Getting the right beam sizes. And so here's an example from Arup, Singapore, Marina Bay Sands. It's much main hotel, but just outside there is a museum with a sort of the structure looks like a bit like a flower, opening flower, and this is quite a complex braced moment frame. Now, with moment frames, you change the stiffness of one element, it attracts more load, and so on. And so they're using optimization routines, which they wrote themselves, running with the GSA model, and you see that the plot of the weight of the structure, and they achieved optimization at around about 100 iterations to get down to the final answer there. And you see the weight saving goes from about 6,000 tons down to about 1,000 tons. Big improvement. And yeah, Marina Bay Sands did the main hotel as well, and just sort of throw this in because it's such an amazing image. That's the swimming pool on the roof of the hotel, and you consider that roof is spanning between the towers, and so that is basically one large beam, and the deflection control on that beam, as you can see, is quite tight by the water level along the edge of the infinity pool. If that deflection hadn't been taken into account, well, you would see it in the water level. Okay, another shape optimization technique we can look at: optimality criterion methods. Shape optimization or size optimization is normally about working out which individual size it needs to be, but that's much a strength option. Optimum criterion method, or OCM, can take into account deflection as well. So what we're doing here is we want that every part works as hard as every other part by using the strain energy, and then we can then adjust the strain energy in all the elements together to optimize for the deflection. And here's a result of this exercise done on this mega column braced core. And you see the blue line is the tonnage and the orange line is the displacement. So they're achieving their target displacements whilst reducing the tonnage. If you just look at strength, what you tend to find is deflections get too large, and then you have to boost up the materials to get them back again, and it can be quite tricky. So, topology, shape, size, and everything. If we look at something like Pierre Luigi Nervi's Gatti Wall Factory, is that topology optimization? Is that shape optimization? Is it size optimization? Is it a bit of a mixture of some or all of them? Don't worry too much about the exact categorization of what optimization you're doing. Just bear in mind there are lots of things you can be doing. Oh, time is short. I shall speed up a bit. Right, so there's the various methods. Let's look at some methods you can use, some heuristics. Heuristics are recipes and that sort of thing that you can use to optimize your structures or other designs. So, deterministic methods. I mentioned calculus, and here is a pictures of Newton and Leibniz, who both co-invented calculus all those years ago and then argued horribly about it. So I like simple examples. Imagine you can define the formula of the structure as y equals x squared. How do we optimize it? Well, we can look at where is the lowest point on this line. So we can differentiate to find the slope of the line. And so the slope is 2x. We know the zero slope is when that is equal to 0. So 2x is 0. That gives the answer x equals 0. And so we know the lowest point, or the zero slope, is on this line here. Is that a maximum or minimum? Well, if we differentiate again, we can see it's greater than 0, so we know it's a minimum. Great. Another example, y equals x cubed. Differentiate lowest slope, 3x squared. Again, zero slope is at 0. But if we differentiate again, the change is actually equal to 0. So it's neither max or min. It's a point of contraflexion. So we can use calculus to help optimization if you can define the formula. And a more recent example, you want to build a reservoir. It holds 10,000 cubic meters of water. And we've got the height and the length and the width to play with. In this example, I'll say the length and the width are both going to be the same. So we can say the height is a function of the width, and we know the formula for the area. We can substitute them together. We can differentiate that to find this expression, put this equal to 0, and we can find the answer is the minimum amount of concrete on the walls and base is when the width is 27.1 meters and the height is 13.6 meters. And just to check, differentiate again, we find it's greater than 0, and therefore we know that is a minimum and not a maximum volume. Yeah, now that's not always an option. Sometimes we need to iterate and look again until we get to the final answer, a bit like design in general. So here's an example. There's there's this variable frame, there's a point node at the top. We just initial guess, put all the sections the same size, so all have the same stiffness, and we'll then get this distribution of bending moments and axial forces, which means that then if we then design this, the n columns will get a higher load, they'll end up getting stiffer. So they'll attract more load, and we'll iterate through until we get to an unbalanced. We get to an optimal structure for that one load, but as I'm sure you all realize, heck, the wind comes from other directions. There are gravity loads on this structure, and there's all sorts of things that we haven't considered. Similarly, if we start off by giving just random sections, we end up with a completely different final answer. The load path changes and all that sort of thing. So yeah, the initial sections can be crucial, but how do we avoid these problems? Well, we look at multiple load cases simultaneously, optimize them all at the same time. We can group sections together to make sure similar sections have similar sizes. If we've got wind from both directions, we make sure the structure is symmetrical, and various tricks like that to make sure you end up with a sensible final answer. Alright, Newton again, this time Newton-Raphson. So yeah, we talk about the slope of the structure, and interesting to note that if you're doing a finite element analysis, the stiffness matrix will actually give you the slope of the structure, or the tangential stiffness, if you want to be particular. Newton and Raphson, they'd come up with this idea that you could find the roots of equations or where things cross and everything by picking a point, finding the slope, giving a new point, and just keep iterating until you get to the answer, or at least near enough within engineering tolerances. And the better guess you start with, the faster you get to the end answer. The faster it converges. All good. Can be good. Can be terrible. These slopes, either for equations or real structures, are not always smooth. If you remember the design space image from earlier, and sometimes if you start off with two starting points which are close together, due to the complexity of the slope, they can suddenly diverge and give you very different answers. Now, Newton-Raphson is a non-linear analysis option, and it can be very quick, or it can be terribly slow, depending on the structure and where the starting point of the analysis was. Okay, next one. Now, talk about slopes and everything. There's the hill climb or gradient methods. Now we call it hill climb. Normally, optimization is finding a minimum, so it's really finding going down rather than up. But yeah, you can just multiply by -1 on the answer. So we want to climb up the slope, or climb or go down the slope to find the bottom. And generally we're looking at either the slope of where we're at, we have our initial guess, we look at the slope, which is the direction for most efficiency, or alternatively just poke blindly around so we can find what's the better option around us, and we can then find our way down the slope until we get to the bottom or the top, depending on how you think about it. And that can work very well if you've got a nice single peak. But there can be multiple peaks. Imagine, you're trying to find the highest peak in Britain by starting somewhere like Guildford, for example, and just walking uphill from Guildford, you'll get to the Hog's Back. You won't find Snowdon, you won't find Ben Nevis, and so on. And likewise, in this equation here, if you start off over here, you get to that peak. Over here, you get to that peak. If you start in the middle, it's flat. Imagine starting in Norfolk and trying to walk uphill. It's not going to work. Where you start from is important. And each stuff, if you are looking at complex design spaces, there are ways to use artificial neural networks. Give it a few example points. Neural networks eventually will approximate the surface, and you can then optimize using the neural network to find the peaks that way. It can be a useful shortcut. Now, gradient methods can be very fast. So here's an example. Our compost steel beam software. The gradient here is just the steel sizes, and you start with the lightest size and you keep checking until you find the first section which works, and that is definitely the lightest section. And gradient methods like that can be very, very quick. Don't always work, but in cases like this, very efficient. As I said, they are not always the fastest. I'm answering my own question here. So what else can we do when gradient methods don't work very well? They're not efficient. We can start to use randomness, stochastic methods. How might these work? So simulated annealing, which you may have come across. I'm sure you've heard of annealing. So annealing based on the way that metal stiffens as it cools and so on. In simulated annealing, we use a hill climb method plus a random element. Now the random element is we just pick another point in the design space, somewhere else, a distance from our current point, and we have a heat factor which says how far away that point is, and if that new point we find is better than where we are, we then move to that point, we increase the heat a bit, and we choose again. But if the point we choose is less good than where we are, we reduce the heat a bit and stay where we are and choose again. The idea here is that initially you get very large jumps around the design space, and you explore in the design space, and as you begin to find the good locations, yeah, you're in the Welsh Mountains, you're in the Scottish Highlands, the temperature starts to reduce. Hey, you're in mountains, and hopefully you'll then focus down onto the Ben Nevis, the Snowdon, the Scafell Pike. Of course, there's always a risk you might find another peak which is nearly as high, pretty good, but yeah. With stochastic methods, nothing is ever guaranteed. You should find reasonable answers. You can't guarantee you'll find the best answer. Other methods, Monte Carlo method, always a gamble. How might this be used? So Monte Carlo method originally created by the scientists working on the Manhattan project, and they wanted to. They had their equations. They had a range of variables, and also they couldn't just blow up thousands of bombs to test them. So they thought, well, how is it typically going to behave? And they realized with the early computers in the 1940s, they could give the random values into the variables and see how things typically work. And in this example, I've used this method to try and estimate value of pi. A square, circle in the square, random points. Is the point inside the circle? Is the point outside the circle? That gives us an idea of the area of the circle versus the square. And we know the formula is pi r squared. And so we get an estimate of pi. In this case, 100 points. I get an estimate of pi of 3.04. Reason close? Not close enough. Do it with 1,000 points. Hey, I'm actually hitting 3.14. Just ignore the additional decimals and also ignore how many times I had to run this to actually hit 3.14. It's more accurate. Now, how might we use this in structure engineering? Imagine you're looking at the likely behavior of a structure under vibration. When doing ultimate limit design, you're looking at ultimate conditions, worst cases. That's worst case, that's not so typical cases. Lowering stiffness or higher stiffness, it will change how things work. And you might use Monte Carlo with all the tolerances and everything, see how things are likely to happen, and so on. Now this is a one shot, but we can build on Monte Carlo by using genetic algorithms. Genetic algorithms take a Monte Carlo simulation as a starting point, look at each of the answers it finds, choose the best ones of those, and then uses those to find more answers, hopefully better answers. How does this work? So, imagine you got, it's based on theories of evolution and crossbreeding. So we've got two possible answers. These two answers, these points, design answers, design spice locations, they give good answers, reasonable answers. So we take them and we crossbreed them to give a new design. And this can work quite well. Now, slight downside, we need to actually model these answers as binary, but we'll come back to that. So here's an example. The fitness of these values is of these purple squares is how close are they to this point in the middle. Yeah, it's quite arbitrary in this case, but there is an optimal design. I know it's here. I'm just modeling it. Okay, so four possible answers, and we can take each of these answers and say how far away they are, and we can then give them a fitness value, which is based on distance in this case. This real structure model, it'll be the weight of steel work or the embodied carbon or something like that. Now, you know, these coordinates, I had to render them in a binary form. And so these coordinates give us a binary number, which, and you see the 0, 0, 0 is 0, 1, 0, 1 is 5. We stick them together, it gives us our genome, the DNA of the point in the design space. We have a fitness, we have a percentage, we call a weighted roulette wheel, and we choose each of these answers based on these percentages randomly. So pick two answers, this one and this one. I will then crossbreed them by cutting them at a random location, okay, in this case straight down the middle, and so we can see, and then swap over the two bits. So you can see 0, 0, 1, 1, 0, the 0, 0 is there, and the 1, 0 is down there. We end up with two new coordinates. Now, this cutting point doesn't have to be in the middle, it can be anywhere along. And we can also randomly mutate one of those bits just by flipping one of the bits randomly, and we keep repeating this until we've got a new generation of answers. And surprisingly enough, even this example, 3 of the points are actually now much closer than their parents, with one over here actually going off somewhere else. Yeah, they're not guaranteed to be optimum, but you think this point over here, waste of space. But that's because we know that there is only one answer and it's right here. You're doing a real optimization, you don't know where the optimum is, and the genetic algorithm can start finding and start honing in on the location over here, but the best answer could be over here, and these runts of the litter can carry on exploring space, and they might find a better location in the design space, a better design, and prevent the premature convergence of the optimization. So here's an example from Eindhoven University. So what they're looking at is optimal geometry of tall building facades with bracing and minimum weight and minimum number of elements. And so start with the random population, rank them, select two parents, crossbreed them, repeats until sort of hone on an answer. And because we've got both weight and number of elements as target optimization, they end up with a Pareto front with a choice of layouts, and at which point we can then go, oh, architects, which one do you like the look of best? Because aesthetics can come in here. So obviously aesthetics, you can't put a number onto aesthetics. You need humans for that, but other things with numbers, the computers are very good at. Other biologically inspired optimization, particle swarms. Less well known than genetic algorithms. Now, this is inspired by the swarming of bees, the flocking of birds, that sort of thing. The way they work together to search area, keyword search, to find things they're looking for. In their case, food. And then if we take vultures, for example, you often hear about vultures circling around. That is quite a deliberate policy. In their case, they're actually signaling to the rest of their family that they found something. But anyway, particle swarm is inspired by that sort of behavior. And what we have instead is a particle, a point in the design space, which is flying through the design space. So it has a velocity, a velocity vector. It's at a point, it has a velocity. It also knows the best answer that it's found. So it has a vector towards there. It knows the best answer found overall. So it's a vector over there. We do a quick sort of vector summation, maybe with some fiddle factors in there, which then gives us a new velocity, a new point to move to in the design space in the next step. And so in theory, all the points sort of circle in and zoom in on the best answer. That's the theory. I've done a test, and you can see this plotted here. The red line, or the red spots here are the best here. So best spots. So I find that they all tend to circle around. One of them might zoom in, but the rest tend to explore around the area. And with all these optimizations, we want that balance between exploration and the which is keep on searching the design space, and the exploitation, which is sort of zooming in and focusing in on the final answer. And you see the blue one is sort of exploiting that space and sort of searching close into the optimums. Okay, another biologically inspired method, ant colony optimization. So ants, they appear dumb to us because individually they got virtually no brains, but en masse they can demonstrate quite amazing intelligence, and they do this by communicating with each other by making changes to their environments. Now this is called stigmergy. In the ants' case, stigmergy, they lay little chemical trails, pheromone trails, and these pheromones have different pheromones for different meanings, and they communicate through these chemicals. And so what happens then is that an ant comes along, detects some of these chemicals, and depending on how strong they are, they're more likely to go towards the strong sense left by its sisters. It's a little bit random, it's not definite, and also crucially, these chemicals, these pheromones, evaporate over time, which means the stronger they are, either the more ants have been that way, given the same signal, or they're more recent, or possibly, well, a combination of the two. So as this works, so imagine you've got a nest and you've got food, and one ant has found the food, and there's these various paths back, and it's coming back to the nest in a slightly random way, leaving a trail which says, I found food. Other ants spot the trail, follow the trail up, they find the food, they grab the food and come back to the nest again, leaving the same trail, and what you find is quite quickly the ant trail focusing on the shortest path, because shortest path, the chemicals are more recent, so they're a bit stronger, so you get more ants going that way, so that gets reinforced and so on, and the ants are very efficient at finding the optimum paths, with the occasional other ants still going random route, carrying exploring, so that they're exploiting the route back, focusing on the optimum, with some exploration still happening. Now, this is a route finding algorithm, and can be used for general route finding, but you can also use it for looking at general designs as well. So if we take the design space and have each dimension as a range of options, so a bit small text here, there's depth and there's height, there's orientation and various factors, heating and cooling and so on. There are a series of points through the design space, and the design choice is then a route through the design space, and they can use ant colony optimization to quickly search all those various options to find the optimum answers, looking at all these various different objectives. So, question for you. How do you feel about using randomness in your designs? Is that something you'd be happy with? Do you feel uncomfortable? Yeah, it's some people, it can freak people out, but randomness can be a very powerful tool in your armory. So, conclusion. Look at the time. Remember, types of optimization problems: continuous versus discrete, unconstrained versus constrained, none, one, or many objectives. Yet you can have optimization with no objectives. Probably not for us. Deterministic versus stochastic. I would always start with deterministic, but you might need to use stochastic. And the type of structural optimization, topology, shape, and sectional size. And these are now in the correct order to start with. Then there's the various heuristics, deterministic, calculus, and so on. You follow these, you'll get to the same answer each time. Stochastic, or random, you should get to good answers, but these can find answers that these can't. And be honest, what I would recommend doing is maybe using combination of the two. You can use stochastic methods and the deterministic to polish it and so on. But of course, beware of diminishing returns. And also think about optimizing optimization. Remember the two steel beams. Have you got a design space of 100 by 100 beams, 10,000 possible answers, or 20 by 20? Only 400. Big saving in time and everything. Choose your method carefully. One method might not be as efficient as another. Genetic algorithms, very trendy, can be horribly slow, but they can also be very efficient. So also think outside the box. As the case of the salesman here. Selling on eBay can be a lot quicker than actually going from city to city in the shortest way possible. So, again, question for you: what should you be doing regarding optimization? We need to achieve zero carbon construction, and I think optimization is one of those tools, along with reuse, reduce, recycle. Well, reduce aspects that we can be doing to achieve zero carbon construction, reduce costs for our clients, produce better designs overall. So I mentioned, my book does have a large section or 2 chapters on optimization. Go into the details, methods a little more detail, and I must say it's had very good reviews so far, which we've been very happy about. And at this point, we've overrun time a little bit, so I failed on that criteria. Hey, we're unconstrained. We haven't hit 7:30 yet. So I'll say at this point, are there any questions?